Om Shri Sai Ram. Seeking Bhagwan's divine blessings, I welcome one and all to the second day of the two-day international webinar on Physics for Healthcare organized by the Department of Physics, Sri Sathya Sai Institute of Higher Learning. Today, I am here to introduce the first speaker of the day, Dr. Shuvan Prashant Turaga, a senior research and development engineer, Attonics Systems Private Limited, Singapore. Attonics Systems is a startup dedicated to realize fast, portable, and compact spectrometers for multifold applications. Sir is actively involved in product strategy and development teams of the Attonics Systems. He is also a key member of algorithm development and signal processing teams. Dr. Shuvan is one of the prestigious alumni of Sri Sathya Sai Institute of Higher Learning. He completed both his BSc and MSc degrees from our very own institute. Then after, he obtained his Doctor of Philosophy from the National University of Singapore. He was working on the area of terahertz optics and metamaterials. He developed two-photon lithography system and terahertz time domain spectrometer and also designed metamaterials for designer dispersion using coupled structure. From July 2015 to January 2017, Dr. Shuvan was a co-founder and tech lead in Kiranam Labs Private Limited. This startup's aim was to commercialize visible light communication, also known as Li-Fi. Then after, Sir joined as a research fellow at the National University of Singapore, where he worked on the area of diamond photonics. In 2018, Sir joined the Attonics Systems as the Senior Research and Development Engineer. Sir has a deep interest and passion in physics and engineering, and he wishes to be a part of photonics revolution using light to solve world's problems and make it a better place to live in. Today, Sir will be sharing his knowledge on the topic compact, cost-effective, and portable spectroscopy solutions for healthcare. Now, I request Dr. Shuvan to deliver his talk. Sairam.
Yeah, so it is first of all a very humbling experience to be a part of this esteemed webinar where all the greats are presenting something related to healthcare and diagnostics, and with the platform being physics. And I'm sure the talks have energized all of us, and I hope it makes everyone very interested in healthcare as well as diagnostics, because given the nature of pandemic and everything which has started recently, healthcare has become a huge industry by itself, and it is not only going to be the mainstay. Also, it is going to determine how we move forward in terms of even economy, because everything is determined by how we cope up with this pandemic. So, without further ado, I would like to then start with my presentation. Let me just share my screen. Can you all see the presentation?
Yes.
Okay.
We are able.
Okay. Okay, so the title for my talk is Compact, Low-Cost, Portable Spectroscopy for Healthcare. So I got an opportunity of joining the startup in 2018 when I was a research fellow in NUS, and I was working on spectroscopy. What interested me was that we could develop spectroscopic solutions which can then go to a customer or could be used in on the field rather than in the lab. So that was my motivation to join the startup, and I learned a lot when you look at from an academic angle and versus an industry angle, how different the solutions look like. You get that perspective, and this is one of those opportunities, I think, that also changed my outlook and understanding of things. How physics could be a major um, um, marker for transforming any particular industry, because it is such a broad it has such a broad applications, and that you cannot you would be surprised that you don't find something you can apply physics on. So that's the reason I joined the startup. And so here the main idea is our vision. So I'll just go with the overview, wherein I'll just briefly introduce Attonics Systems, why Attonics Systems was started, and then a brief introduction on spectroscopy, just to give you how you can do a visible spectroscopy with our spectrometer. And then colorimetry is the science of measuring color, and how to estimate colors is very important in our day-to-day. And although these topics are very simple, you would have probably learned most of this in your 10th class, but it is interesting how industry applies them every day to give you the products that you use in your hands. Taking a mobile phone, for example, you have plastic appliance. Any electronic appliance has a color on top of it. So all these color-based QC is done by a spectrometer. So colorimetry is a huge field by itself. And then I will delve a little bit into healthcare applications. So first and foremost being dental care, wherein dental care is one of the active projects we are involved in, wherein we are developing a dental shade scanner. So dental restorative surgery is a topic of interest, because many people get teeth replaced, and often what happens is when you get your tooth replaced, you want to get a replacement which looks similar to your other teeth, and that's a color problem again. So how do you find the right shade for your tooth? That is interesting. And then I'll also just very briefly show you how spectroscopy can be applied for skin care and other diagnostics. And also for plants. Plants is interesting again, because food security is a huge issue in 21st century, wherein we want to know where our food comes from, what is the food quality, and what is the food freshness. And just to tell you how a simple spectrometer can tell you how good a leaf is, can go a long way in determining how good the crop will be at a future date. So, and how good your food will be at a future date. So, same thing applies to food freshness. For example, ripe fruits. How do you tell? Generally, it's easiest metric of finding whether fruit is ripe or not is how the color changes, right? So, for example, a banana changes from green to yellow, and apple also, when it ripens, when it becomes older, you can see the color change. So every thing around us is made. We actually visualize it with color. So color is a huge a metric to determine how good or bad a substance is. So it's easiest of metrics, but also very difficult to determine precisely. So, so the vision for Attonics Systems was it's a 5-year-old company right now, and the vision is to become a world leader in high-end affordable microspectrometers. So it started all with the PhD of my CTO Sasha, who started out with a project in his PhD wherein he tried to shrink FTIR spectrometer into a micro FTIR spectrometer, wherein he shrunk the size by at least 1,000 times. So with that starting point, there was no looking back. He continued working for 10 years on this. And now we have products which have been translated from lab to something which people can hold in hands. So, when you have something which you can hold in hands, your application, the gamut of applications that you have are enormous. So you can use it for anything on the field with the portability and with also you need to of course ensure that it is cost effective. Otherwise, it doesn't reach a wider audience. So water quality testing, food quality, any kind of quality assurance, if you want, you need spectroscopy because spectroscopy is easiest way to find whether a particular molecule is present or not. And that's the way you ensure that a particular criteria is satisfied or not. So that is the vision for Attonics Systems. So to give a brief overview of spectroscopy, right? So what is electromagnetic spectrum? So it stretches all the way from X-rays and to microwaves. But what we look at or is probably the visible, which is the smallest part of the entire electromagnetic region, which is just 400 to 750 nanometers. And little bit on the left is UV, little bit on the right is infrared, right? So for this talk, I would just concentrate in these three ranges, UV, visible, and infrared. But these ranges are basically considered as optical ranges. Visible is the one which is visible to our eyes, but UV and IR are non-visible. So generally, the detectors for these are, they're all made of silicon or germanium, depending on the wavelengths, or in gas, for example. So these detectors allow us to analyze light coming at it. So now with this understanding, we look further as to what kind of conventional spectrometers we find in lab, right? So spectrometers are just devices which allow you to break down light into its components, and then you measure the different frequencies and you estimate how these different frequencies are distributed, right? So there are three different types. One is a filter-based spectrometer, then you have a diffractive or dispersive spectrometer, and then you have an interference spectrometer. So filter-based spectrometer is probably right now with you when you are using a smartphone, a camera, for example. It has an RGB sensor inside it, which is red, green, and blue filters sitting on a silicon sensor. So that's the easiest way to reproduce color and also to find out what color the scene has, right? So these are filter-based spectrometers. So they just select a certain band and you measure how much light is present in that band. Everything else is rejected. So this gives you a very easy estimation of what light, how much of light is present in how much range of wavelengths, right? So then diffractive or dispersive spectrometers are typically based on separating light by wavelengths. And interference is based on modulating light based on a phase delay and then establishing the relationship between intensity and phase delay, which is typically called an interferogram. And then you recover the spectrum through a mathematical operation. So that is how an interference spectrometer works. I'll just go a little more deeper. So filters, for example, red, green, and blue. You can see the blue filter, the green filter, and the red filter. These are typically used in all kind of color cameras. So even your eyes have red, green, and blue cones, which I'll again tell you a little later. And that's how you perceive color, and that's how color appears to human eyes. So this is the easiest way to tell, okay, we have this much of red, this much of green, and this much of blue. And that's how you say, okay, this is probably the spectrum. But again, this is a 3-channel spectrometer. So if you want a little more precise understanding of what colors are present, you have um, much more precise filters, which are again called thin film filters, or they are again based on concept of interference. But these interference filters allow you to have very narrow bandwidths, and then you can utilize this interference to get the intensity in a narrow band of light. So for example, what you see here, this is very narrow band, and you can tell very precisely at a particular wavelength how much light is present, right? So, but these filters are again very costly. But colored filters, for example, the RGB, which is on your phone as well, is very cheap. So moving on, there is diffractive and dispersive spectrometers. So diffractive is basically based on grating. So you have some lines ruled on a grating, on a piece of metal, and when you reflect with that, you have higher orders of dispersion because of the periodicity of the lines. So this is the concept of diffraction. You all may know it. And dispersive is generally by using a prism. This was one of the oldest spectrometer known, because Newton used it to find, okay, the white light which we get from the sun is made of few colors. Of course, the oldest spectrometer would be rain droplet, because that's how you see rainbows, right? So that's the understanding of diffractive and dispersive spectrometer. So these basically break up light into different components, and then you can easily measure them spatially as to what is the component of light and how much of it is present. So the problem with this is that it can be very high resolution. It can have good um, what you call like within a narrow bandwidth it works well, but it may be compromised in terms of high bandwidth. If you're looking at high bandwidth applications or light throughput, you will have issues because you lose a lot of light. When you use a diffraction grating, for example, you lose it to different orders. So typically they use a first order, and the zero order contains at least 30% of light. So you lose right away 70% of 30% of light. And yeah, so and prism generally, because whatever material you use is gonna absorb little bit of light, and that absorption is going to reduce the amount of light received by your detector. So again, these two methods have their own challenges. And the third method is interferometer-based spectrometer. So here, what happens is you have a scanning mirror. So it's a typical Michelson interferometer setup. It can be any other interferometer as well. They have tried different types of interferometers, but just to showcase how a basic concept of interferometer is, we have here a Michelson here, wherein light comes in straight, and then you have a beam splitter, and then you have two different arms. One of the arm is constant, and the other arm is has a moving mirror. So this scanning arm allows you to measure something called as interferogram. So if you look at this, so the interferogram is basically a measure of light intensity versus the displacement of mirror, which is basically increasing the phase in the light. And this phase actually plays the role of modulating the light received at the detector, and that's why you see this. So with this modulation, if you were to do a Fourier transform, you can recover the spectrum back. So this is how typical Fourier transform spectrometers work. And this is the case of a monochromatic radiation. Let's say now we add extra light into this, or additional wavelengths, right? So here we have, let's say, three different wavelengths. And now you will have an interferogram which doesn't look like a sinusoid. It will look more like a couple of sinusoids mixed together. And now if you were to take a Fourier transform of that, you would, based on the Fourier transform, you would recover a spectrum which has three different spectral bands in it. So the advantage of interferometer-based spectrometer is that the light throughput is the maximum you can get. As you can see, you receive almost an entirety of light, and you have something called as multiplex advantage. So detector receives all the light. It's just that it doesn't differentiate between wavelengths. It only differentiates the phase. So, and this information is now mathematically converted into spectrum. So this also is known as nowadays there's a new term for this called reconstructive spectroscopy. So reconstructive spectroscopy means you are not measuring spectrum literally. So in other cases like filter based spectrometers or diffractive or dispersive spectrometers, you are measuring the spectrum, which means every light channel is every detector channel is measuring a specific part of the spectrum. But here you are measuring the entirety of light. It's the white light which is falling on it. But because of the phase delay, you can recover the wavelength aspect of it through a mathematical process. So this is the introduction to our spectrometer. So this is where now if we were to put all these spectrometers on a chart, on a common chart of say cost versus performance, right? So filter-based spectrometers are the cheapest because you have just 3 filters or 4 filters define how much uh, information you want, and then you can define those many filters. And so it's most affordable and most portable. So many sensors are generally based on this. And performance-wise, of course, it's the least precise option because you then have only information of uh, the number of filters that you have. That's the information you have on the spectrum. So it's low cost, but it's very useful for simple applications. So then you have dispersive grating. So this is a mainstay of all the spectroscopy done today because grating spectrometers are easy to make, first of all, and the resolution achieved is very good. And typically you scan the grating to get a higher bandwidth. But the problem with this device is that it is very costly. So grating-based spectrometers, typically any lab-based spectrometer will range from 2,000 to 10,000 US dollars. Here, yeah, it's about if you were to use for especially color-based measurements or even like very high accuracy QC, you might read even higher. You might have to even pay higher amount of money. So then the third part is like Fourier transform. So these are FTIR spectrometers. These are very bulky. They are huge. They take up the whole bench space, and they have a huge scanning arm. And the scanning arm determines what resolution you get. And so all these spectrometers are very precise. They are very good for measuring infrared spectra, for example, but they are very costly as well. They typically cost about $50,000. And again, it depends which wavelength range you're looking at. If you were to go towards mid-infrared or even higher ranges, it gets even more costlier because of the detectors. So where does Attonics position itself? So Attonics is making these phase delay lines in a very small form factor. It's like an interferometer built on a chip. So what you're getting is some kind of low-cost alternative for the FTIR, wherein you have large bandwidth, and it is fast because there is no scanning arm, and it's rugged, and it is the smallest form factor. So how does that work? So you basically shrink down your interferometer into a small chip which has multiple delay lines, which is carved out by X-ray lithography, and this is our patented technology. And this chip then sits on a detector, and then that's how we have our portable spectrometer. So the advantage of this is your spectrometer itself, the module itself, is as big as a chip. The size of this particular device that you see here, this is our latest offering. It's called AttoCube. is predominantly because we have put in extra LEDs to shine light on anything, and I will give you a demo further down. But yeah, so this is the spectroscopy is literally on a chip. So that is the biggest advantage, and there are no moving parts. It's all a static device, and you get high spectral resolution because it's an interferometer after all. And when you use a grating, for example, or a prism, as soon as you start reducing dimensions, you start losing resolution because you cannot draw two fine lines, right? On a grating, for example, and prism, when you start shrinking the prism, your dispersion becomes much lesser, and so because of that, you cannot really get a very high resolution when you shrink the size. So that's the advantage of getting an interferometer on a chip, wherein you get best resolution at low cost. And these chips are made at wafer levels. So you can get at least 100 to 200 chips on a typical 4-inch wafer. So that's the advantage of Attonics. So this was pioneered by my CTO, Sasha, who worked on this for like almost his 15 years of his life. And finally, this product has come from lab to the market. So there's just to give all students understanding, always when you do things in a lab, when you do something in your PhD, what you're doing is cutting edge or frontier research. But when you want to translate that to common man, it takes a lot of effort to make it simpler, make it easier, make it more scalable, and make it cost effective. So it takes a lot of time to come through all this and then make a product out of it. So that's the usual what you call as roadmap from technology which is in a lab to technology which is in the industry and to the common man. So that being said, so we are trying to get something which can fit our pockets. So just to show you how the chip looks like on a CMOS, this is how the chip looks like. And when you scan the wavelengths across, you get a different interferogram every time. And when you convert it back, you get a monochromatic spectrum. So this is a typical monochromatic spectrum from our device. And so talking about miniaturization is a huge topic in spectral sensing nowadays because spectrometers are always seen as bulky devices, and these devices are, if they were to be made portable, they can be used for different applications, and they can be used to do QC on the go. So, so the whole part here is because of high costs associated with spectroscopy. Many people don't use the spectroscopy for QC. They use much more simpler QC methods because they are fast and reliable. But spectroscopy can give edge over the precision or accuracy of your QC, which other methods cannot give. And so the drive is towards miniaturization. So as I said, if you look at miniaturization as well, there are lots of different techniques tried over the past few years. This is a image from a review paper which recently came out, in which again they describe it into the same similar kind of sectioning, which I told you how you differentiate between different technologies. So you have dispersive optics, narrowband filters, then they separate, of course, the Fourier transform and the reconstructive spectroscopy. So ours is kind of at the bridge of these two, or the cusp of these two, wherein we use interferometer as well as reconstructive spectroscopy. So, so presenting our device, which is the AttoCube, it just fits the palm. So I have one here with me, and so the wavelength range is from 380 to 1000 nanometers, and the optical resolution achievable with this is 12 nanometers. Repeatability, which is useful for finding, say, atomic lines or even the laser lines, is very high because we are using an interferometer at the base of it. So this is literally spectroscopy from lab to pocket. So this can really fit a pocket. So the example applications where this kind of tool can be used is multifold. So if you look at it, you have color measurement, you have food freshness and quality. How can you measure freshness of vegetables? So imagine a person using this daily to see whether his salad is fresh or not, or whether his food is adulterated or not. So imagine what all applications can come through that. Then lighting measurement. A lot of even production video production units, they use lighting measurement tools to establish, okay, this is the light I have on the scene, and this is how I will change my exposure. And so for LED manufacturing, for outlets wherein they which are selling, for example, clothes or apparels, right? You want to have the best kind of lighting so that people can distinguish colors. It might have you might have noticed that when you go to an outlet where there is low light, you will not be able to distinguish between certain shades of blue or certain shades of green because of the light that is falling on the apparel. So that itself is a science in itself. So light measurement is a huge topic. Then counterfeit detection. Then semicon industry also uses spectroscopy to measure their processes. How plasma, for example, plasma etching is a process which is used for etching wafers. And to find the end point of a particular process, they use spectroscopy. It's called optical emission spectroscopy. Then you have skincare. Skincare is again finding what color your skin is or how good the health of your skin is. You can determine by finding the molecule of your choice. So melanin, for example, is responsible for how what your color is, and then moisture tells you how good the skin's moisture content is. If you have not drunk enough water, for example, your skin starts showing the signs of low moisture. So this is one way of finding whether you have also some kind of skin cancer. So there are multiple applications in skin. Then hair care. Hair care is a huge industry. So for example, when you color your hair, how do you know which color will you get? Especially in fashion industry, or celebrities, when they color their hair, they need to know exactly what color it will result in. And because of bleaching or coloring your hair also undergoes a lot of damage. And this damage can be established by looking at the spectrum of the hair. So, and agri-tech is again based on determination of plant health, and for example, soil analysis. Then academia and research, there are lots of general spectroscopy applications which academia is interested in. So these are like a huge number of applications. So it's like you have a hammer, and these are all different nails that we can hammer them on. So that's why spectroscopy, or in general, even physics, has huge number of applications. So, and in addition to this, we also offer something called as AttoCore. So this is just our MPA chip and a CMOS detector. So this is something which we offer it to our OEM customers who can then integrate it into their devices. So moving forward, so this is our software, and this is like any other spectroscopy software, and it's used for measuring the spectrum. You get the spectrum chart here, and then we have a color chart as well. I will also give you a small demo on color measurement with my device. So just to show you how it works. And just to give that demo, I need to just brush up your basics on spectroscopy. So spectroscopy is nothing but measuring color or measuring wavelengths intensity versus wavelength, which is the spectrum, and you have typical spectrum measurement is just directly measuring the light source. Reflectance is measuring the reflectance of a surface, and transmission is with some sample in between, and you measure what is the transmittance of that sample, right? So for reflectance, typically you measure dark spectrum, then you also measure the spectrum of the light source, which is known as the bright spectrum, and then you get your reflectance by by dividing spectrum over your measured spectrum over bright spectrum. So that is the reflectance. So color measurement is basically, again, it's a huge field in itself. So to I'm putting it very briefly here. So the whole science of color is to understand how our eyes perceive color. So our eyes actually have three different cones, which are sensitive to three different bands of light, which is red, green, and blue. And that these cones are responsible for measuring the colors, and then our brain puts it together to say, okay, this is the color yellow, this is the color blue. And this took a while, and there were so many standards which came in between how to understand or perceive color and how to communicate it. So typically what is done is, to give a short intro, you take a reflectance of a device and of a surface, and then you multiply it with an illuminant, and then you multiply with the measured functions of these cone responses, and that's how you recover X, Y, Z. So these X, Y, Z parameters are called tristimulus parameters, and these are the chromaticity indices, literally, which is telling how much of light is seen by each cone of your eye. And this XYZ can then be further converted to RGB, which we all know how an RGB works. So all your screens that you're watching this presentation on are RGB screens. So RGB is very simplified version of how your eye perceives it in terms of measuring R, G, and B in 0 to 255 levels, right? So that's RGB. So it's a very what you call basic understanding of how light measures something. And the same RGB is again used in a color camera, wherein it sees R, G, and B, different intensities of R, G, and B, and then puts together a scene which is colored. So that's how color science works. So this is a typical color chart which is used for doing QC. So just to show you how a device works, so you see that every color here. So one is gray tile. You have some kind of response which looks like a broad white reflectance. So it reflects everything like a white. Whereas blue, for example, will only reflect blue. Green will reflect green. Red will reflect red part of the spectrum. So that's how color works. So when you see red, you still have some more computation to go from spectrum to this color which is presented on the screen. So let me show you how that works with a simple demo. I hope you can see the screen here.
Yes, sir.
Yeah, okay. So this is our spectroscopy software, which is called AttoView. And if you can see my camera, let me just put this here. So this is the same chart that I showed you just before here, right? and this is our device. So the device has LEDs built into it, and I can show you. You can see the LEDs glowing here. Can you see it? And so right now I'm trying to measure light from this color chart. So I have light falling from the spectrometer on this, and what I measure is the light coming off from the surface. So there's a spectrometer at the end of this device at this point, and you have LEDs built into this part. And all along you have optics which convey the light back to the spectrometer, right? So you can see here different colors. You can see how they show up on the right side of the screen, right? So that's how a typical color-based spectrometer works. So you have a spectrum. So spectrum looks like this. And a white spectrum is basically the light of the spectrum of the light, which is from a white surface. So this is how I have LEDs, which are white LEDs. So this is how they look like. And when you put it on any colored surface, so this is red, for example, or yellow, this is how it looks. So you can see on the left side, the spectral plot. On the right side, you see the color. And the same thing, if you were to see the reflectance, then it's based on how much is reflected back based on the white light. So white light would be somewhat like 100% line. And then if you look at blue, green, red, you see each reflecting different parts of spectrum. So that's a very brief presentation on the color. And also, of course, you can measure the skin color or hair color. So hair color is, I don't have much hair left now, but yeah, so this is very handy. It can fit the hand of um, um, any person, and then he can put it anywhere he wants. So this is basic presentation of our device. Let me now come back to the PPT and show you just a few applications. Okay, I hope you can see the yeah. So we had a quick demo. So now we come back again to something which is more interesting. These are applications which are used for day-to-day needs, right? So this is dental shade scanner. So we got this project because there was a problem in aesthetics of dentistry. So aesthetics is a huge field in dentistry wherein you try to restore teeth. And when you restore teeth, the problem always is if a person has a tooth replacement, the dentist finds it hard to find a tooth which has the right shade, which is matching the other teeth in his mouth. So it's a huge industry because every tooth restoration in India, I checked up with a dentist, it costs around 20,000 rupees per tooth. And what happens typically is that a dentist you pay a visit to the dentist, you ask him for a change of tooth, and he measures your tooth, typically with a shade chart, which is seen here. And the shade chart tells you, okay, this is roughly here, based on you put the shade chart against the tooth, and you try to visually tell what is the shade of your tooth. But what often happens is when this goes to the clinician who makes the tooth with materials like ceramic, with zirconia, he puts together a tooth which probably has slightly different color or shade. And when you put it back on the on your teeth profile, you would see that this shade doesn't match. And it's a huge problem because what happens is when any person goes to a dentist, he has to visit at least twice or thrice just to get the color shade right. Now, if we were to solve this problem, how would we do it? So we need a measurement device which can measure the shade of the tooth, and the dentist needs to have it, and the clinician needs to have it. So there's a huge problem with color communication between dentist and clinician because the shade chart looks different in the different colors, the different lighting. So if the dentist were to measure your tooth with the shade chart on a rainy day, versus when on a sunny day, he will have a very different uh, shade selection. So whereas that problem of shade selection is eliminated once you have a spectrometer, because that will measure it precisely. It will give you a more accurate measurement of tooth. So so that's why we went on this project, and it was a very useful application wherein we could make a difference in terms of the problem is really huge, and this fits very well with our colorimetry, because we are trying to establish how to measure colors. But in this case, the solution space is in kind of measuring colors for teeth, right? So you have so what does this dental shade scanner comprise of? It has a diffuse reflectance probe with built-in LEDs and a spectrometer. So you typically, it's our usual spectrometer core, which is we also call as Atto core, and then you have a reflectance probe here, and you can see our CTO measuring this shade chart, for example. So what happens behind the scene? So you have LEDs coming through, lighting up the fibers, which are then used for lighting of the tooth. So the same thing as what you saw here, wherein I showed you how a spectrometer converts spectrum into color. It shines white light and it receives the reflected spectrum and it converts it into color. Same thing is done here, except that teeth are like 4 mm by 4 mm. It's not really huge. So you need to have a smaller probe. So the way to confine light into a smaller space would be to use a fiber. So that's why we have a reflectance probe made of fibers. We have a collection from the central portion, and you have fibers which are lighting up the edges. And generally, tooth is a very hard material to understand, because tooth is made of two things. One is enamel and dentin. So you can see that any kind of translucent material always scatters light within the material itself. There's a light scattering within the material. So that's why the tooth color is not just the color on the surface, it's a whole tooth itself. So it's a huge, again a very big topic in itself, and there are lots of publications on this to establish how to get the right shade match. And it changes with material to material. So if you were to do this with now zirconia, or you did with ceramics, you will get very different results, because very different spectra, because both are different materials and they scatter light differently. So this is a typical measurement of the shade chart, and you can see here. So we have measured LAB. LAB is again a measurement standard recommended by CIE, which is the authority on colors. And LAB are just like RGB. Think of RGB in a different coordinate system. So LAB values for the 5 of the shades. If you look at it, so our spectrometer has very less error in estimating these shades, and you can see the precision of it. So typically, you can see the main thing, the main problem with teeth also is that it's not just color; it's just probably just a very small color space. In the color space, it's like within white to yellow spectrum, right? So it's very precise. Uh, a very precise shade would be hard to obtain. So moving forward, just for giving you some more applications for skincare, we can do, as I said, skin tone measurement, effectiveness of sunscreen, or for example, if you apply a sunscreen, do you get UV protection or not? Then whether you have if you have an allergic reaction, can you measure based on your skin color? Then moisture in your skin also gives a lot of information of the health of your skin. And skin melanoma is a huge topic again. It's a then oxygen concentration and um, um, even heartbeat, for example, you can actually measure if you put the spectrometer on your skin. So, just to show you a very simple demo. So this is um, a measurement of heartbeat from our spectrometer. So we just measure the light coming back from the finger, and if you analyze it and put a Fourier transform on it, because it's a temporal scan, you can get the heartbeat of the spectrum, heartbeat of your temporal intensity. So you look at the intensity of blood. Blood is generally reddish, so you have around 600 nanometer peak. So you measure the intensity of that over time, and then you take a Fourier transform. This is a very easy way of showing how your typical health bands measure your heartbeat, right? So this is just a showcase. So the same way you can also measure the blood deoxygenation and oxygenation. This is very interesting because this was used a lot for determining whether patients had enough oxygen in their blood for COVID diagnosis, whether a COVID patient had lung failure. The only way to determine that is using a pulse oximetry. So we also thought, okay, let's try it out with our spectrometer. So what we did is we put a rubber band on one of the fingers, so that stops the blood flow. So because of that, what you see is the blood is having lesser oxygen, and you can see that the oxygen level starts dropping as soon as you start measuring after this. And at some point, we break the rubber band, and you would see that the oxygen measurement will go up. So this is the hemoglobin with oxygen. So at some point, it will break, and at this point, you start seeing there's a peak of oxygen going up. So this is again a very simplistic demonstration of how you can use these kind of spectrometers to do everything at home, and you can use it for different purposes, get different metrics, and it's a healthcare diagnostic device. So, and plant health diagnostics, I'll just give a very brief intro. So plant health is again, if you have a leaf or something, you can tell based on the color of the leaf as well, how good a leaf is. So generally, I just got 3 leaves here to showcase. So for example, a good leaf will have higher chlorophyll content, little worse will have lower chlorophyll content, and the worst will be something which has no chlorophyll. So chlorophyll is again a huge marker, is a big marker for determining how good a plant is, and that helps people determine if the plant will survive or not, and also tell what kind of stress it is under. So um, so chlorophyll leaf fluorescence is again easy way to determine. So we had done some studies on this, but I'm not presenting it here, but wherein we can see that when you when you bleach the chlorophyll and then you let it decay after that, and you again check the fluorescence, what happens is the leaf recovers back at some point. So the recovery rate, if it is good, that means the leaf is fresh. If the recovery rate is bad, that means the leaf doesn't have enough chlorophyll, and that's why it is failing. So there are ways to put these metrics into action, and to find whether your crop is going good or not. And so just to tell about our team, so it's not just a single person on this whole project. I've shared the work of all of our team here. So we have 2 founders, Sasha and Philip, and then we are supported by many other people. So Prof. Moser is the brain had was the brainchild or had the brainchild of this spectrometer, and he was the PhD supervisor of Sasha. And then we have other team members who work on different aspects of it from manufacturing to product development to data analytics. And I'm a physicist, and I'm involved in different stages of this in different roles. So I'm kind of a jack of all trades, and I see myself in developing this product further with the team, and I enjoy it thoroughly. Thank you so much for your time, and I'm open for questions if you have.
Sairam.
Sairam, sir.
Sairam, Dr.
Sairam.
Prashant, it was definitely very wonderful to hear you, to see that sea change that has happened in the transition of use of spectrometers.
Exactly,
Almost
yeah.
3 orders of reduction and just
Yes.
a handheld unit. And say, in your own words, you have said from lab to pocket, which is just a wonderful thing to have. In one of your slides, you mentioned that there is definitely a reliability, or rather reproducibility is there.
Right.
My question to you is, you also mentioned, say, for example, when you're talking about the dental part, that
Yes.
the color changes, or rather, we perceive
Yes.
in a different way when we see on a sunny day and on a rainy day.
Yes.
That is the visual perception.
Correct.
So in such condition, how do you say that your unit will have a reliability on the data accumulated or captured?
Yes. So yeah, we are working actively on it, and we also are presented with these challenges because. So one thing for sure is the reason spectrometer works the way it works is it has its own light source, and we measure the reflectance based on the light source. So you are as good as you measure the light source. So the accuracy is then based on how accurately your spectrometer prints out the data from the reflectance. But reflectance is not enough here. So what happens here is if, yeah, as you said, the ambient conditions can play a role. So
Yeah,
for
that's
that,
very important, because we are used to using Perkin-Elmers and so on. The cavity is closed, so
correct.
there is a controlled exposure of light to the object. While
Correct.
here we are keeping it at ambient situation, so there will
Correct.
be interaction from outside. How do you control that, or have you taken, maybe you have taken care? But
Yes.
what I meant is, today I do a measurement at 10 o'clock. My
Yes.
same measurement at 4 o'clock may vary on the same sample.
Correct. Yeah. So what happens here is when we measure it. So one thing we ensure is that we uh, take care of the dark spectrum, as I said in the beginning. So dark spectrum is not just detector electronic noise; it also involves the scattering noise which is present. So you remove the dark spectrum, and then so that makes the measurement a bit more absolute in that regard. It takes care of the ambient conditions when you're measuring it, and also there are other smaller changes that we also take care of. For example, if you were to use this tool, you can use it in a little without a direct overhead light, for example. So and we found because the light source is right on the tip of the probe, you don't have much loss. So you basically recover the light coming from the probe rather than any other light, because that light from the probe is the strongest. So you don't see any other light coming there. So, and your oral cavity itself, so if you were to measure this on tooth of somebody, oral cavity itself acts like a dark cavity. So it helps in that way, because you're measuring against the tooth, and you try to put the tooth scanner, and at the background you have a black background. So that's how we take care of it. And there are definitely challenges, but not something which is impossible to circumvent. Yeah.
That's one more question. Now,
Yes.
your unit, as I see it, basically, I would put it like that, it is very good for what we call the analytical measuring tool, colorimetry.
Right.
Yeah. And
Right.
so do you think you recommend that today the colorimetry, which is a wet analysis, can be
Mhm.
replaced by your unit?
Yes, yes. So in fact, I've not presented.
Can we recommend it as an analytical tool for college level?
Yes, I think so. I mean, right now the way we are marketing this is more to do with day-to-day needs of spectroscopy, but it can become more and it can become more accurate if you have if you were to have a little more precise, a better detector with more control over it. So it becomes a little more bigger then. But again, if you want to use for day-to-day measurements, just want to check how the sample is, you can still get very accurate results with it. It's just that uh, at some point your cost versus efficiency, right? You have to draw the line. So what exactly you want to do, then you have to specify, and then based on that, we can check whether it measures it or not. For example, if you were to use something like a PMT for a PMT and a monochromator for doing spectroscopy for analytical work, that may not translate directly to this device, because this device is something which is meant to do portable readouts, and the sensor here is a silicon sensor, which is not at the same level as the PMT. So that's why the challenge is always between the cost and the portability of the application. And if you want to include precision, you can go up to certain level. You cannot push the limit beyond certain limit. So analytically, I would say for colorimetry, it can be done. For fluorescence, sometimes this may be a challenge. And for colorimetry, actually, we are working with few groups wherein they have analytes which change color because of a reaction, and then we measure the color change for them. So we have done those kind of studies. We have also done, for example, chlorine bleaching measurement. How much chlorine, for example, they use chlorine to clean the pools. So if you want to know how clean the pool water is, how do you know? Generally, the way they do it is they add a particular chemical, and the chemical changes color. So it's any litmus test, for example, changes is based on the change of color. But now, if you were to use a colorimetric sensor, you can get very precise change of color, and then you can say you can put a better number of concentration of your molecule or analyte, and then say this is the right color, or this is the right concentration I want to measure. Yeah.
Thank you.
Thank you. Thank you. Regarding other questions, so Manoj has asked how color value is obtained from spectrum. So spectrum, as I said, becomes reflectance, and then is converted to uh, um, XYZ coordinates, and then to RGB or LAB. And Akhil has asked what type of LEDs have been used. The LEDs are generally white LEDs. So white LEDs have actually, there's no coherence actually. These are incoherent sources. So, and so peacock feather pigment is brown in color, but it shows different colors due to the structure. Will the spectrometer be able to determine these differences? So spectrometer generally is measuring a composite color. So it may not be able to see these differences. It depends on how far you're looking at it or how close you are. And the angle and the way you collect light, it's the same way how you look at peacock feather, right? So the angle of light which is incoming will change your perceivance of the perception of the color. Then does the output of the device change in case of sunlight and in artificial light? No, it doesn't, because I mean, you can use this for measuring the light source itself. And the way we measure it is we always measure it where it blocks the light from outside. So it is completely blocked. And that's how you ensure that there is no external light when you're measuring it. Then how accurate are the results of the Attonics spectrometer? So I showed you the results for a typical color metric chart. in which so the red and the blue line. So the blue line is a typical grating-based spectrometer called, we have taken Otto, and this is how our spectroscopy measurements look like. So this is for the different colors, and you can see here. So it is not used for IR and UV right now because our the manufacturing, the way we have done it, is meant for visible, and it extends to near infrared. So it is more or less limited by our sensor, which is from 380 to 1020. So then I think, yeah, so interference has, so in this case, right, so interference is the nature, here you're not using a laser for interference. So it's not related to that. It's not related to the coherence length of LEDs. So you are using, you are measuring how the light passes through the structure, and then you're measuring what is the output of that structure, and then you're translating it back to a spectrum. So the structure itself produces a change, as you saw. Yeah. Over the prolonged period of time, the performance of the detector may start to degrade. Yeah, so generally the performance of detector, as far as we have seen, it doesn't degrade so much right now. I mean, we don't see the degradation on the detector itself. What we see is on the LEDs. So LEDs have a typical shelf life of 10,000 hours or something. So after that number of hours, it starts decaying. So generally, I mean, so far we have not seen, yeah, some kind. We have not seen a degradation in the output. That's it.
Sairam, sir, I'm
Sir.
sure there will be a lot more questions, but due to shortage of time, we will take the other questions later. So I
Okay.
thank you, Dr. Shuvan, for your wonderful talk. And I'm very thankful to you for taking out your valuable time and being with us today, sharing your knowledge and experience with all of us. Thank you very much, sir.